Hello, I'd like to try to make a video about the inverse of sine, cosine, and tangent. First, let's look at the functions. Sine looks like something like this. You start with a line going up like that, and then we have it coming up like that. Now, the inverse of sine. If you turn this up, basically if you take that diagonal and just flip the paper along that diagonal, that's the inverse relation. And I want to make that distinction, relation. And the relation for sine, it's still got that that slope in the middle, looks the same way. And but it's going to look something like this. So that is the inverse sine relation. Now, the thing about this, it's not a function. So what is generally done by your calculator is it cuts this off right here and right here. So your calculator will give you a function arcsine, which has a domain of -1 to 1, because that's the output here. And range, it just goes just this part. Basically, it looks like that. And this is going to be pi over 2 and -pi over 2. Let's look at a circle for a second. The sine function. The sine function is actually, if you put theta in here, sine theta, well, let me put sine theta over here. This length here, if this is 1, this length here is 1, then this is sine of theta. And as theta goes around, it goes up to 1 and down to 0, down to -1 and up to 0, up to 1, down to 0, down to -1, up to 0. So 0, up to 1, down to 0, down to -1, up to 0. So that is what sine actually is. And you can go around the circle over and over again and have and you get the different values. Meanwhile, cosine is this distance here, with this value at 1. Cosine of 0 is over here is 1, and cosine of pi over 2 is 0. So this cosine function, running out of room, I'm going to have to turn pages. Okay, so the cosine function looks like, so let's draw our line for the 0 point, and we'll draw a straight line right there. And then from that straight line, we'll go down and up and down, down and up, down. It's just, okay, straight is not a good word. This was a straight line. This is a horizontal line. This is a sloped line. So this is what the cosine function is, and just like the cosine, it has an inverse relation that goes like this. Making sound effects for it. The is the sound that that any function makes actually. Okay, so this is 1, -1, 1, -1, and that's the cosine. Okay, tangent. How can I describe the tangent? All right, well, the tangent, as you go around the circle at angle theta, the theta is, or tangent theta is equal to sine theta over cosine theta, and it is the slope of this line. And so let's think through this is the angle is pi over 2, pi, -3 pi over 2, and we'll be going around as theta goes around, the function will look something like this. We'll start with 0. As it turns out, at this point, sine theta has a slope of 1, cosine theta has a slope of 0, but the value is 1. So you can use something called L'Hopital's theorem to find out the slope of tangent theta. I won't go into it now, but I'll just say that the slope of the tangent there in the center is 1, but it quickly goes, as this line goes around from here to here, the slope at this point is infinity. So it's going to go like that at pi over 2. And at negative pi over 2, the tangent function is going to go down like that towards negative infinity. And then it repeats as you go past the vertical. The slope goes back to negative infinity again and comes up around pi or so we got going around, it goes 0, pi over 2, the slope is positive infinity. Then we go down this way. That seems like the slope would be, oh, no. Here the slope is negative infinity, isn't it? Goodness. Okay, it goes here's positive infinity. This is positive infinity. This is negative infinity. So it goes immediately from a slope of positive infinity to negative infinity. Then it comes around to 0 to positive infinity. Then pop back to negative infinity again. 0, positive infinity, negative infinity, 0, positive infinity, negative infinity. Okay, so that's why it goes like that. It does that sudden discontinuity there where the slope goes from positive infinity to negative infinity. So that's the tangent function. All right, so now algebraically speaking, what we can do with our sine and cosine, if we talk about the inverse function, let's say we know that sine theta equals y. Okay. So I like to use y here for this, and I'll use another circle to say cosine theta equals x. And what I'm going to do here on the sine theta equals y, I'm going to draw a straight line across here. This is my value y. And then we will have two solutions, one here, theta, and the other one is pi minus theta, because this is pi, and then we're going to move back an angle of theta from that point. So that is theta and pi minus theta. Okay, and so we actually can take that as a set. Y, theta could be arcsine of y. That's this solution here. That's arcsine of y. Arcsine of y is not a true, is not the inverse relation. It's a function representing a small part of the inverse relation. So this is arcsine y. This angle here is arcsine y. But it could also be pi minus arcsine y. And it could also be, we could go all the way around the circle with theta and add 2 pi to that. So 2 pi plus arcsine y. Let's actually say, yeah, 2 pi plus arcsine y and 2 pi plus pi minus arcsine y. So 3 pi minus arcsine y. And you can continue with that pattern using some value like k representing integers. So instead of 2 pi plus arcsine y, let's call it 2k pi, or k times 2 pi, because it can be 2 pi, 4 pi, 6 pi, 8 pi. And here we can go 2k pi plus pi, 2k pi plus pi minus arcsine y. So you can again have 2k or 2 pi, 4 pi, 6 pi, 8 pi, and that would be the way to represent the entire solution set. With cosine theta, you do the same thing, except here we'll put x, and in this case, the angles are theta here, and this one's much easier because here there's a symmetry around the 0, so we just have theta equals arc sine y, I'm sorry, arc cosine x, that's this one here, and we'll have negative arc sine x. So theta equals plus or minus arc sine x, arc cosine, sorry, theta equals plus or minus arc cosine x. And you can do that once again with 2k pi plus or minus arc cosine of x, and that will give you the entire set of solutions, theta, that you can have. With the tangent, you will find it repeats very, very regularly. So if we have theta as our solution is arctangent of, I'll call it m. M is the slope. Arctangent of m being the delta y over delta x. Then the next one is just 2 pi plus, no, it's, yeah, it's 2 pi, because going pi, no, it is pi. It is exactly pi. This is pi. This is, so this is 0, this is pi. This over here, the crossing point is 3 pi, because the slope is going to repeat every half cycle. So you'll basically have k pi. So your solution set is going to be k pi plus arctangent of your slope, delta y over delta x. Okay, so that is pretty much the inverse functions for sine, cosine, and tangent. Inverse relations for sine, cosine, and tangents. And semantically speaking, you don't have inverse functions for sine, cosine, and tangent. You only have inverse relations because these things are not functions. I'm sorry, this one is not a function, and this one is not a function. So those are inverse relations, but the arcsine function is not really a true inverse of sine. It's because it only represents this part of the function. Okay, thanks for watching. Ta-ta for now.